We're going to go into the next part of permutations, which is permutations with restrictions. Let's take a look at this example. Permutations of n distinct objects with restrictions. So there are 4 people, Dev, Ed, Faye, and Gui, D, E, F, and G, are going to sit in these seats on a plane. Faye must sit by the window. That right there is a restriction. Now you're told in how many different ways can they sit. So what this means, there are 4 seats, 1, 2, 3, and 4. And we are told that Faye is already at the window. So who are we left with? Dev, Ed, and Gui. Therefore, for that first seat, we have 3 options, Dev, Ed, and Gui. Then they are going to be chosen. So for the second seat, we'll have 2 options, the 2 that are remaining. And for the third seat, we'll have 1 option. And then to find the total number of ways, we just multiply them together. So we have 3 times 2 times 1, which is 3 factorial, which is just 6. So there are 6 different ways that they can sit on this 4 seats. Next, we are told to find the number of ways of arranging 6 men in a line so that A, the oldest man, is at the far left side. So again, there are 6 men, 1, 2, 3, 4, 5, 6. And the oldest man is here. Therefore, we are left with 5 men and 5 spaces. And the way they can be arranged in those spaces is just 5 times 4 times 3 times 2 times 1, which is also 5 factorial, which is going to be 120. That means there are 120 ways of arranging these 6 men such that the oldest man is always at the far left. That's for A. When we go to B, we're told that the 2 youngest men are at the far right side. So again, we have 6 spaces, 1, 2, 3, 4, 5, 6. And we're told that the youngest men are at the far right side. Now, the spaces that we have left are 4, and we have 4 men left, which is just going to be 4 times 3 times 2 times 1. So you'd think it's just 4 factorial, right? But these 2 young men, we haven't been given restrictions as to which one has to stay in the second position from the right in the line, and which one has to stay in the first position from the right. So these 2 can switch as well. And if you name them Y1 and Y2, we have either Y1 and Y2 or Y2 and Y1. Because we have 2 people, Y1 and Y2, and there are 2 spaces, which gives us 2 times 1. So this will just be 4 factorial times 2 factorial, which gives us an answer of 48. That's for B. Then in part C, we are told that how many number of ways are there of arranging these 6 men if the shortest man is at neither end of the line. So we have again 1, 2, 3, 4, 5, 6. And so we're going to group these men. We're going to have the 5 men that are there and that short man that's there. Firstly, we will choose the last spaces with these 5 men. So 5 and 4. So because you choose one of the 5, then that person is gone. So now you have 4 options left. You're going to put them, you're going to put that guy in the other end. Then what we can do is play around with the middle area. And for now, we can just do the 3 men that are left, the 2 men that are left, the 1 guy that's left, and then the short guy that's there. We're going to name him S. And so what here we have to do is just 5 times 4 times 3 times 2 times 1, right? Which is just 5 factorial, right? Because there are basically 5 spaces, 1, 2, 3, 4, 5, because 1 is taken up by the short, the guy in the middle. However, this short guy, as you might have thought, can be in this position, or in this position. And obviously the position that he's at right now. So when we get 5 factorial, that's not it. That's just the ways of arranging these 5 men and that short guy if you say that the short guy can only sit in this place. But he can sit in 4 other places. So there are going to be 4 other options where the short guy will be sitting here, and sitting here, which means we will take that 5 factorial multiplied by 4, because we just have 5 times 4 times 3 times 2 times 1 arranging the 5 men. And that last guy can be in 4 different seats. So we'll multiply that entire thing by 4. And we get 480 different ways of arranging for C. Next, we're told to find how many ways that 2 mangoes and 3 watermelons can be placed in a line if the 5 fruits are distinguishable. meaning they are all distinct items, and the mangoes must not be separated. So currently we have mango, mango, watermelon, 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 and they are placed in a line where there are 5 spaces, right? But we're told that these mangoes must not be separated. So the trick here is we need to keep them together. We count them as one object. Okay, then we have our second, third, and our fourth. So now actually we have just 4 spaces because we have reduced the number of items as well. So here normally we would just take one of the 4. So we have 4 options for the first one, then 3 options for the second, then 2 options for the third, and 1 option for the last one. And we're just going to multiply them together. So 4 times 3 times 2 times 1. Because they are distinguishable. So we don't have to divide by any factorial to sort of cancel out the watermelons because they are 3 W's, right? However, these mangoes, because they're distinguishable, you can have mango 1, mango 2, like that they are placed next to each other. Or you can have mango 2, mango 1, like that they are placed next to each other. So that 4 times 3 times 2 times 1, you're going to take that and still multiply it by 2. Because that's the ways these 4 objects are placed in that line. 4 objects, why? Because we group the mangoes together. But those 2 mangoes can also be switched. So that's why you multiply that by 2. There are 2 possible ways that the mangoes can be placed, which are these 2. And here what we get is 48. So there are 48 arrangements for part A. For part B, the trick we're using is this one right here, where if you want to arrange things with restriction A, that will be the same as finding the total arrangements subtracted by the arrangements with the restriction of the complement of A. You use that information for part B. So if you want to find the number of ways where the mangoes are separated, then what you can do is find the total ways of arranging subtracted by the number of ways that the mangoes must not be separated. So not separated. So here, what are the total ways? We just have 5 spaces. Then 5 times 4 times 3 times 2 times 1. So the total is 5 factorial. And we just did the not separated, which was 48 in part A. So we'll subtract 48 to that to get the number of ways where they are separated. And this will just give us 72 total arrangements. So there are 72 total arrangements where they are separated. And there are 48 total arrangements where they are not separated, which gives us a total number of 120, which is 5 factorial. Now, suppose you are told to arrange R objects from N objects. So currently we have been given 5 objects and 5 spaces, or 4 people and 4 seats. What if you have 7 digits but only 3 places? So for this, I'll do it in 2 ways. One, using this formula. And I'll explain that formula with the other way, which is more practical, which is the way we have learned it up to now. So there are 3-digit numbers. So we have 3 spaces for possibilities of numbers. And we have 7 digits. 1, 2, 3, 4, 5, 6, and 7. Therefore, there are 7 options in the first one. There are 6 options for the second one. And there are 5 options for the third place, which gives us 7 times 6 times 5 as our answer, which is 210. You can use this formula for this as well. N, you have the P letter in your calculator, then R. What N is the total number of objects, which is 7. What P is the permutation symbol, which in my calculator is if you press shift, then the multiply function, and you get the P like this. Then that R is the number of spaces that we have, which is 3 spaces. And what this does is it gives you N factorial divided by N minus R factorial. So in our case, it is 7 factorial divided by 7 minus 3 factorial. So 4 factorial, right? Which is just 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by 4 times 3 times 2 times 1, which what happens here? That this last place cancels out, which leaves us with 7 times 6 times 5, which is exactly what we got when we did the logical approach. So here even the answer is going to be 7 times 6 times 5, which gives us 210. Then we're told, in how many ways can 5 playing cards from a standard deck of 52 cards be arranged in a row? So we have 5 playing cards, 1, 2, 3, 4, 5, and we have 52 cards in total. So the logical way, 52 options for the first place, 51 options for the second, 50 options for the third, 49 for the fourth, and 48 for the last one. Or we can write it like this: 52 permutation 5, because there are 5 spaces. And both of these would give you 311,875,200 total ways of arranging those 5 playing cards. Finally, the last 2 examples. In how many ways can 4 out of 18 girls sit on a 4-seat sofa when the oldest girl must be given one of the seats? So again, currently we have 18 people, but we have 17 girls and 1 oldest girl. And we have 4 seats, 1, 2, 3, 4. We're told that that oldest girl has to be in one of these seats. So she can be in the first one, the second one, the third one, or the fourth one. And then what we have left is 17 girls with 3 possible spaces, because one of them is taken by the oldest. So as per what we just learned, it's going to be 17 permutation 3, because 17 objects and 3 spaces. This is going to give us 4,080. But we see that we have 4 options for that. So we'll multiply that by 4, which will give us 16,320. I can explain this again, which will sort of cement the examples in the previous parts as well, where I did the multiply by 4 and multiply by 2 and all that. But basically, the girl, the oldest girl, can be in the first seat, the second seat, the third seat, or the fourth seat. So there are 4 possible options. For the first possible option, for the other seats, we have 17 for the second one, 16 for the third one, and 15 for the fourth one. Similarly, 17 for the first one in the second option, 16 for the third one, and 15 for the fourth one. Similarly, this, and finally this. We have 4,080 arrangements in the first option where the oldest girl is at the start. We have 4,080 arrangements in the second option where the oldest girl is in the second seat. We have 4,080 arrangements in the third option where the oldest girl is in the third seat. And we have 4,080 arrangements in the fourth option where the girl is in the fourth seat. And in total, we have 4,080 times 4 total arrangements, which is 16,320. Finally, in how many ways can 4 boys and 3 girls stand in a row when no 2 girls are allowed to stand next to each other? So this is another trick that's used as well, where you have to know this for your future questions. If you have 4 boys and 3 girls, you would assume there would be 7 spaces, obviously, right? But in this case, we want the 2 girls not to be next to each other, any 2 girls. And so for that, we're going to do something else where we're going to give 9 spaces actually. 1, 2, 3, 4, 5, 6, 7, 8, and 9. But we're not going to fill all of them, obviously, because we have 7 possibilities, right? And what we're going to do is put the boys in such a way where the girls will never be next to each other. So boy here, boy here, boy here, and boy here. 4 boys are done. And any girl will not be able to be next to each other. And so we have arranged it in such a way where the girls will be separated. And here we have 4 boys with 4 spaces. Therefore, there are 4 options for the first space. Then there will be 3 options for the second space, 2 options for the third space, and 1 option for the last space. Which we also get from 4 boys, 4 objects, and 4 spaces in total, which will give us 24. Similarly, if we do 4 times 3 times 2 times 1, which is the same as also 4 factorial, right? Then the girls, there are 3 girls, but there are 5 spaces. Obviously, we can't do 3p5 because the number of objects has to be greater than the number of spaces. But what we can do here is switch it around. We can assign one of these spaces to one of the girls. So instead what we do is we make the spaces as objects. So we have 5 objects and we are permutating it among 3 girls, which will give us 60. Then, because this is still in the same arrangement, remember the other ones were in different arrangements, right? Like we had 4 different options. This is still that only option, right? We were just arranging them in that one scenario. So we don't have to add these two. We have to instead multiply them, as we have discussed earlier. So 60 multiplied by 24, which gives you 1,440. So there are going to be 1,440 total ways of arranging the boys and the girls in this restriction here. So we have learned the different tricks that are there for all possibilities when it comes to restrictions. You just have to use each one of those tricks for each scenario that you get in your tests.